Hello, this is a presentation on DIFUZZRTL, which is a paper about differential fuzz testing for CPU RTL. To me, what I liked most about this paper is their discussion on metrics for measuring coverage in hardware, because this is something that we're used to almost taking for granted in software, where coverage is very easy to define and measure. But they show that for hardware, there's actually a lot of nuance in your metric for coverage, and the most obvious way you might think to do it actually turns out to be a pretty bad abstraction that they end up building off of and then improving. So the part I really want to focus on in this talk is not just the details of how they use differential fuzz testing to fuzz CPUs, but the more interesting conceptual point they explore, which is what hardware coverage should even mean. So I wanted to start out this talk with a quick hypothetical. Imagine you have a CPU design and you want to verify it because you know that once you ship it, mistakes are really expensive and embarrassing. So you use a fuzzer, which naturally sounds pretty appealing because you can generate a lot of tests automatically and then use coverage as feedback and to let that guide the search, hopefully being able to fuzz the entire design and rule out any bugs. So now imagine your coverage cooks and then tells you that you have full coverage over this design and it wasn't able to find any bugs. So excitedly you go and tape it out, and then you put it out in the market, and much to your dismay, there are still hardware faults and a bug appears and you're left wondering what went wrong. So this question of what went wrong is pretty easy to answer for software fuzzers. Usually it simply means that your fuzzer never generated the test it needed to actually show this bug, and your input space just wasn't explored enough. But also sometimes it could be a bad oracle. Maybe your reference model that you're comparing to was buggy, that type of thing. But for hardware, there can be a third kind of insidious reason, which is that there was bad coverage. And what I mean by that is the fuzzer may not have missed the bug because it failed to generate the right test. It might have missed it because its notion of progress was wrong. And that's kind of the surprising claim of this paper, that it might not be anybody's fault besides the coverage metric. So first I'll present a pretty natural way to represent coverage using an analogy from software. So imagine you have a switch statement and then you have a bunch of cases, and a natural way for a fuzzer, a software fuzzer, to recognize and track coverage for this is by kind of tracking which of these paths are executed during the run of a program, and then kind of over time you build more and more complete coverage because you're visiting ideally all of the cases of this switch statement. But there is a very natural hardware equivalent to that switch statement, which is a multiplexer. So for a multiplexer, you're usually taking many inputs, and then you have some select bits, which are going to decide which of those inputs get routed to the output. And you can see that it's very similar in that the control value chooses which of the inputs ends up passing further into the digital circuit. So then, because we have these analogous structures, it seems very natural to just try to translate the approach from software directly to hardware. So by that I mean, just like in software where you reward kind of exploration of various cases, you can reward the fuzzer in terms of its coverage by exercising new control choices over the various multiplexers in the design. But as you might suspect, there is a high-level issue with using a branch-like view to measure hardware coverage. And this is because a branch-like view says these same local decisions happened, but doesn't have any time component, so it can't separate between coverage of A, B, and then C versus B, then A, then C, even though the exact sequence of the states often defines behavior in hardware. To concretely illustrate why this time component is so critical when measuring hardware coverage, I decided to borrow this example from the paper with a memory controller that can receive data from flash and DRAM, SDRAM, and I'm starting with just flash for simplicity, but in this model, the CPU is able to accept 8 bits per cycle, and flash is able to provide the memory controller 8 bits at a time. So it's really a pretty simple system. You can see that it's starting in cycle 0 in this ready state to indicate that it's ready to accept a byte, and then it transitions into a busy state as there's data inside the memory controller, and then finally it transitions back to a ready state once the transfer to the CPU is complete and it's ready to take in another byte. It goes back to a busy state, and then finally it ends up back in the ready state. So a really nice way to reason about this behavior is by using a finite state machine. So you can see that the memory controller has 2 states, one where it's ready and one where it's busy. And while there's no data, the memory controller will just stay in this ready state, but as soon as there is data, which is indicated by this valid bit of 1, then it will transition into a busy state and therefore no longer be capable of accepting another input. And then in the next cycle, when it communicates that to the CPU, it will then go back to a ready state and be ready for taking an additional input. So the other part of the memory controller, the SDRAM controller, is really similar, except the SDRAM communicates with the memory controller 4 bits at a time. So instead of being able to go directly from a ready state to a busy state, instead it has to accept the first nibble and then be in a pending state for some indeterminate period of time before accepting the next nibble, and then finally can be in a busy state and then ship it off to the CPU and be then ready for a new nibble. So if we wanted to do the same exercise of representing this with a state machine, you can see that we are in a ready state, and then we enter a pending state, And then eventually, once both nibbles have made their way there, we enter the busy state before finally resetting to the ready state. So something quite interesting happens though when you integrate these two well-behaved simple state machines together to make a memory controller that uses both flash and SD-RAM. When you put them together, something pretty interesting happens, which is that one of the states becomes a bugged state, specifically this bottom right corner, this busy first, busy second state, where the first circuit is flash and the second one's SD-RAM in this case. And that case is bad because it means flash is ready with the full 8-bit result in the same cycle that DRAM is also finished assembling its 8-bit result, but the memory controller can only forward one 8-bit value to the CPU per cycle. So at least one result's going to get lost. And it's a particularly interesting example because the bug is invisible locally. It only appears when you look at the synchronized pair, or this kind of Cartesian product of the states that are possible between the two machines. So to hammer this point down even further, now you can kind of see the full state machine that shows the combined state space of both the first and second circuits, and you can see that this bugged state at the top only exists when you combine these two spaces in the to create the product state space. And if I told you which local state each subsystem ever visited, the question is, would that be enough to identify this bug or not? And the answer is no, it's not enough. And to show that, I have an example of a benign execution where in the first cycle, we have the flash going from ready to busy and then back to ready. And then we have the SD-RAM going from ready to pending to busy. And you can see in this benign run, the flash finishes first, and then the SD-RAM finishes one cycle later, so there's no issue with the data being dropped or them competing for the same memory controller byte to the CPU. But here is a almost identical execution, but this does have the bug. So in this case, the two local machines line up so that the flash is in that busy state exactly when the SD-RAM reaches the busy state as well. And because they're arriving in the same cycle, the controller can only forward one, and this is a bug. So if we look back at that natural approach we talked about before to treat hardware more like software, which is how the prior work Fuzz decided to treat hardware coverage, you can see the issue in this example where in either the benign run or the bug triggering run, the exact same toggles occur to the various multiplexers, and therefore it can't distinguish between the benign run and the bug triggering run. It might think that the bug triggering run was covered because it did the benign run, and then your fuzzer wouldn't be able to report or find a potential crash or hardware fault. So to get around these challenges that Fuzz faces, DIFUZZRTL changes what it measures so that instead of asking whether local mux events ever occurred, it asks which control states the design occupies each clock cycle. So in the example shown, the important control state is just the pair state F and state S, so the state of the flash circuit and the state of the SD-RAM circuit. and each cycle that pair is hashed into a state bucket and marked as seen. That's shown on the right side. So now the benign and bug triggering runs diverge pretty much immediately because their state trajectories diverge and they end up hashing to different buckets. So at this point, a natural question you may be wondering is, how do they actually find the control registers, i.e. the registers that hold the states of the various FSMs in the design? And I know when I was reading this, I was wondering if the authors required the designers to manually label those specific registers as FSM state registers. And the answer is no, they actually are able to do something a lot more automatic and clever, where they start with the control signals to the muxes, which are themselves very easy to find. Remember, those are what the baseline works use to determine coverage in the first place. But then they're able to automatically trace that back through simple combinational logic and find the underlying control registers that are actually controlling those muxes. And then once they figure out what those control registers are, they can, like shown earlier, build a representation of the state of the system in any given cycle. I won't go into too much more detail about the specifics of the DIFUZZRTL runtime, but just to make what I showed earlier a little more complete, here is an image that's showing kind of the control registers that have all been bundled up for a given cycle, and then DIFUZZRTL hashes those and then uses it to fill in a particular bucket within this coverage map. And then now this is the final kind of proxy that the fuzzer sees, instead of just the toggles for the various mux inputs like rfuzz and other prior works. So now that we've covered the semantic reason the new metric is better, which is that it preserves that timing sensitive state, there's also a really big practical advantage in that it's much cheaper to use this strategy of the control registers to monitor state as opposed to the prior strategy of the control signals to all the multiplexers, because in principle, one control register may influence many different multiplexers, and if you keep track of that single control register, you can avoid having to keep track of all of those potentially toggling multiplexers that are driven from that particular state. And you could see for the simple example of the memory controller from before, we have the digital logic implementation of the finite state machine on the left. And although in this particular example there's no pair or more of multiplexers that are taking the same state as its selection input, you can see that in a very large design there will be tons of these multiplexers, and it will be much easier to keep track of the state bits instead of kind of the toggles and how potentially quadratically many of these multiplexers are switching on and off. Aside from the coverage exploration, there's also a lot of interesting detail in the paper around sim input, which is how they make differential fuzzing practical for CPUs. And the key idea is to fuzz a structured CPU input, which includes things like instructions, the memory state, and interrupts. And they use that entire structured CPU input instead of just the raw bus traffic like other approaches. So then they can kind of interpret that into a consistent execution and build things like a pseudo memory or pseudo interrupt components so that the same input can drive both the ISA model, like their gold reference model, and the RTL that is trying to implement that ISA. So the paper isn't just proposing a better coverage metric, it's also proposing a much better interface between the fuzzer and a CPU design. So in terms of impact, empirically the paper does pretty well. They find many bugs that were previously unfound in various CPUs, and then they're able to fuzz Boom, which is such a big out-of-order core that prior approaches like RFuzz really struggle to instrument those. The MUX-based monitoring just gets too heavy. And then they have big speed up over RFuzz, as well as a significant reduction in the state, as mentioned earlier, plus lower instrumentation overhead, which is always nice. And in terms of the limitations, there's still a requirement for an ISA level gold model or some sort of comparison target, because after all, it's a form of differential fuzzing, and that means it requires that golden model to compare against. And then also because they're doing differential testing against ISA visible behavior, they're strongest on ISA visible bugs, semantic bugs, and purely microarchitectural bugs are generally very hard for these approaches to find and might require extra assertions or other instrumentation. There's also a mild abstraction caveat. Technically, they choose enough buckets that this shouldn't be an issue, but in principle, you could still have hash collisions where different states collide if you don't have enough states, because the space of all possible states in a large design is just gigantic, and it's possible that a collision could happen, and then you could have a similar kind of abstraction issue as RFuzz, but in practice they don't find much of this. So to wrap things up, I wanted to talk about a more general, broader lesson I took from the paper, which is that abstraction is something that's necessary if you want anything to scale, but abstraction is also something that you need to be very careful about, because it's very easy to destroy distinction you care about using the abstraction, especially if you're just trying to port an abstraction that works in one domain to another one. So for RFuzz, the abstraction was collapse behavior down to did these MUX choices ever happen, in a very software reminiscent way. But then DIFUZZRTL's insight was that for RTL, that throws away too much information, and specifically it's extremely important to preserve these state trajectories over time. And once you have that abstraction correctly in place, everything else kind of falls into place. So that's it.